When dealing with a single quantitative variable, so far we have learned how to construct dot plots, stem and leaf plots, and histograms to graphically display the distribution of our data. This video will take you through the steps of constructing a box plot to graphically display a single quantitative variable. Box plots are very useful for summarizing large data sets and for comparing graphs of a quantitative variable for different categories of the variable. For example, the distribution of student weights by gender. A box plot summarizes a data set with 5 key values, appropriately named the 5-number summary. The 5-number summary includes the minimum and maximum values of a data set, the median or middle value when the data is ordered, also referred to as the 50th percentile, and the values of the first quartile, Q1, and the third quartile, Q3. We will use the data set for the number of hours worked the previous week for 15 randomly selected students with part-time jobs. Here's the data set here. We'll start by putting the data in increasing order. Since we have 15 data values, the median will be the data value in the 8th position when arranged in ascending order. For this data set, the value of the median is 10 hours. The first quartile, or 25th percentile, is the middle value of the lower half of the data set. Since there are 7 data values less than the median, Q1 will be the 4th data value. In this example, Q1 has a value of 8 hours, meaning 25% of the students in this group worked less than 8 hours last week. Similarly, the third quartile, or Q3, the 75th percentile, is the middle value of the upper half of the data set. The value of Q3 for this data is 14, meaning that 75% of the students in this group worked less than 14 hours last week. We'll first construct a skeletal box plot by drawing a horizontal line for the scale. Note that it could also have a vertical orientation. Next, we draw a box whose left or lower edge is at the value of Q1 and whose right or upper edge is at the value of Q3. The width of the box, the distance between Q3 and Q1, is a measure of spread called the IQR, or interquartile range. We then draw a vertical line segment at the location of the median. In a skeletal box plot, the whiskers extend to the minimum and the maximum values of the dataset. Our completed box plot should have a label on the axis and a descriptive title. The disadvantage of a skeletal box plot is that it is not easy to recognize extreme values or outliers. An outlier is defined as a data value that is more than 1.5 times the length of the interquartile range, below Q1 or above Q3. Like on the Sesame Street show, you can think of an outlier as one of these things is not like the other. The value of the IQR, the spread in the middle 50% of our data, for the number of hours worked by the sample of students last week, is 14 minus 8, or 6. To determine if any of the hours worked by the students the previous week would be considered low outliers, we subtract 1.5 times the interquartile range from the value of Q1. This value gives us the maximum possible length of the whisker. Any data values below this value would be considered outliers. Q1 minus 1.5 IQRs yields a value of -1. Since our smallest data value is 2, our lower whisker extends only to 2, and there are no low outliers in this data set. To determine if any of the hours worked by the students the previous week would be considered high outliers, we add 1.5 IQRs to the value of Q3. This gives us a value of 23. Our upper whisker can extend only to an actual data value less than or equal to 23. In this case, it extends to 19, and the student who worked 25 hours has a value that would be considered an outlier. A modified box plot, which we will always construct and henceforth refer only to as a box plot, represents outliers with a circle or asterisk. Remember that the whiskers extend on each side only to the most extreme observation or observations that are not outliers. The completed box plot for our student work hours data is displayed here. You would not include the information in the text boxes. But as we look at this, we see that the whisker extends only to the smallest actual data value of 2, even though by our calculation it could have extended as far as -1. And when we calculated the largest value that the whisker could possibly go to, it was 23, but we only extended to 19 since this is our largest data value, less than or equal to 23, and any other data values, in this case only 25, are recorded as outliers. Recall that box plots may also be displayed with the scale in a vertical orientation. The real usefulness of box plots lies in comparing several distributions. By putting box plots of 2 or more groups or subgroups on the same scale, we can easily compare their centers, shapes, spreads, and any outliers. This comparative box plot displays the weights of a sample of students categorized by gender. The distributions of weights have similar shapes and spreads for males and females, but we can see that females in this group tend to be, on average, about 20 pounds lighter than their male counterparts. And although both genders have weights that would be considered outliers, the females whose weights are outliers would not be considered outliers in the male distribution.